Hi, I'm Zach Shainman,
And I'm Rachel Blair.
and today we'll be going over a differential equation that models an insect outbreak. So this is the form of our differential equation. It'll be carried over on multiple slides as we go over more information, so no need to worry there, but here's just a taste of what's to come.
So just some background information on our project. It's a model for the budworm population over time. It models a logistic growth model, which accounts for the limited space and resources within the population. This is also an example of bifurcation, which we've normally seen for autonomous equations, where small changes in the parameter that's added on to the differential equation usually results in small changes. But for our example, the changes within the parameter are going to have a more drastic effect on the overall solution.
So, briefly going over our parameters, K represents the proportionality constant, which is common throughout a lot of our differential equations. N is the carrying capacity, so the total amount of insects that the environment can hold. P is the budworm population at any given moment. And T is the time in days. So the carrying capacity depends on different variables that we're not going to go into, but things like habitat size and food availability. And the fraction being subtracted off at the end represents the death rate due to predation.
So the equilibrium points that we found for our population model were at when the population is 0 and then when it is very close to the carrying capacity. And then we noticed that the change in the carrying capacity parameter, the equilibrium point, would be very near the carrying capacity and would be a decimal number. And then the classification of the equilibrium points, they aren't very conventional in the way that for the p=0 equilibrium point doesn't really have behavior below it, so we couldn't classify that equilibrium point. But for when p is very near the carrying capacity, we were able to classify it as a sink because the curve is increasing below and decreasing above. And then just interpreting the points, p=0 just represents that we start with no budworms and then the population cannot increase. And then for when p equals the carrying capacity, it hits the carrying capacity and then there's not enough resources to support it, so it just kind of increases and then maintains at that population and then starts to decrease. So just in between the points to the population is just simply increasing to the carrying capacity.
So here's our slope field, and some information behind it is K, a proportionality constant, is equal to 1. Our carrying capacity is 1,000 individuals. The time is a span of 40 days, and our initial condition was 2 individuals for normal reproduction. And some of the slopes are actually pretty steep going up, but once it hits the actual carrying capacity, it levels off pretty drastically and plateaus out. So the effects of some of the parameters on the behavior of the actual function. K prefers integer values. It doesn't really like being decimals less than 1 or decimals in between values of integers. Mathematically, you get some interesting results that way, but as long as it's an integer, it tends to be okay. And K adjusts the overall rate of births and deaths. So the higher the K, the faster the population will grow. The lower the K, the slower the population will grow. N is the carrying capacity, and that simply increases or decreases the carrying capacity. And it cannot be a negative or a decimal because that would pretty much go against the model of the system. And you couldn't have a quarter of a grasshopper or a budworm. And then T determines the time frame overall, and it's actually affected by both K and N. So if K is larger, T would go down because the population can grow quicker, and if N goes up, the carrying capacity raises, so it takes longer for the budworms to reproduce and hit that carrying capacity.
So for our model, we started to put numbers in for the different parameters. And so for K, we put in 1, the carrying capacity we put in 2,000, The initial condition, which is just the starting population, we put in as 2. And then for time, we did a time range between 0 and 40. And then using Mathematica, we found an analytical solution of 0, which would be the equilibrium point P equals 0. And then we also found a numerical solution of 1,999.99, which is like what we talked about before, that the equilibrium point is very near the carrying capacity. And then this is just like a visual of what I just said before, that it starts at 0, increases drastically, and then reaches the carrying capacity, and then kind of just evens out.
Mm-hmm. All right, and then here's our bibliography briefly. Information and sources for images. Thank you very much.
Thanks.